June 1944. A British infantryman lies in a hedgerow ditch in Normandy, 50 meters from a German Panzer IV advancing along a sunken road. The weapon beside him weighs 14.5 kilograms, measures 990 millimeters in length, and fires a 1.4 kilogram bomb containing 350 grams of high explosive through a shaped charge warhead designed to penetrate 100 millimeters of armor plate. The weapon is not a rocket launcher. It uses a powerful spring mechanism to propel the bomb, creating no backblast, no smoke signature, and minimal sound compared to contemporary anti-tank weapons. The soldier braces the weapon against his shoulder, aims at the tank's side armor, and pulls the trigger. The spring releases with explosive force, driving the bomb forward at approximately 140 meters per second, while simultaneously compressing against his shoulder, with recoil approaching 90 kilograms of force. The bomb strikes the tank's hull. The shaped charge detonates. A jet of molten metal punches through the armor. The tank stops. Smoke begins pouring from the hatches. The soldier's shoulder is severely injured. His collarbone may be fractured. He will not be able to use the weapon again without significant pain. The device that destroyed the tank was the PIAT, the Projector Infantry Anti-Tank, and it became one of the most effective and most hated weapons issued to British infantry during World War II. The British Army in 1942 faced an anti-tank problem that was tactical and industrial. German armor had evolved beyond the penetration capabilities of anti-tank rifles. The Boy's anti-tank rifle, standard British issue, could not reliably penetrate German medium tank armor at combat ranges. American bazookas were effective, but required backblast clearance that was often unavailable in hedgerows, buildings, or enclosed defensive positions. British infantry needed a man-portable anti-tank weapon that could defeat contemporary German armor, that could be fired from confined spaces without injuring the operator or revealing position, that required no complex manufacturing, and that could be issued in quantities sufficient to equip infantry sections organically. Conventional shaped charge weapons used rockets or recoilless rifles that produced massive backblast signatures. What British ordnance required was a mechanism that delivered shaped charge warheads without propellant exhaust. Development began in 1941 under the direction of Lieutenant Colonel Stuart Blacker, a weapons designer who had previously worked on the Blacker Bombard mortar. The PIAT's operating principle was mechanically simple but physically brutal. A powerful coil spring compressed inside the weapon's body tube drove a spigot rod forward when released. The bomb was fitted onto the spigot, which protruded from the weapon's front. When the spring released, the spigot struck a cartridge in the bomb's base, igniting a small propellant charge. This charge expelled the bomb from the spigot, while the spigot's forward momentum continued briefly before the spring's resistance overcame it. The bomb traveled forward, the spigot retracted into the weapon, and the spring was automatically compressed by the weapon's recoil, cocking it for the next shot. This system eliminated backblast, but transferred enormous recoil force directly to the operator's shoulder. The weapon consisted of a steel tube housing the spring mechanism, a shoulder pad, a simple trigger mechanism, and rudimentary sights. Total weight was 14.5 kilograms unloaded. The spring required approximately 90 kilograms of force to compress manually when cocking for the first shot. This was accomplished by placing the weapon on the ground, standing on a bracket at the muzzle, and pulling the cocking handle upward with both hands. Soldiers of small stature or insufficient strength could not cock the weapon alone. Two-man teams were standard, with one soldier cocking while the other was loaded. After the first shot, the recoil automatically cocked the spring, eliminating the need for manual cocking between shots, provided the weapon functioned correctly. If the weapon misfired, or if the spring failed to compress fully on recoil, manual cocking was required again, a dangerous and time-consuming process under fire. The bomb used a shaped charge warhead with a hollow cone lined with copper. Upon detonation, the explosion collapsed the cone inward, forming a jet of molten copper, traveling at approximately 8,000 meters per second. This jet could penetrate armor through kinetic and thermal energy, defeating thicknesses far exceeding what conventional explosives could achieve. The PIAT bomb could penetrate approximately 100 millimeters of homogeneous armor plate at the optimal impact angle. This was sufficient to defeat the side and rear armor of most German tanks, encountered in 1943 and 1944, though frontal armor on Panthers and Tigers remained largely immune. Effective range was listed optimistically as 100 meters, but practical combat range was under 50 meters due to the bomb's low velocity and a high trajectory arc. Operational testing began in 1943, with issue to the infantry battalions preparing for the Italian campaign. Initial reactions were overwhelmingly negative. The weapon was heavy, awkward, and required significant strength to operate. The recoil was severe enough to cause shoulder injuries. The bomb's trajectory required substantial holdover at any range beyond point blank, making accurate fire difficult without extensive practice. Most critically, the weapon's reliability was inconsistent. The spring mechanism could fail to compress properly on recoil, requiring manual recocking under fire. The spigot could become fouled with debris, preventing proper bomb seating. Despite these complaints, the weapon was issued widely because no alternative existed that could be fired safely from enclosed positions. Operational deployment in Italy and later Normandy demonstrated the PIAT's effectiveness when employed correctly. The weapon's lack of backblast allowed firing from buildings, trenches, and hedgerows without revealing position or injuring friendly troops in confined spaces. German tank crews learned to fear PIAT-equipped positions in close terrain, where their standoff range advantage was negated. Multiple documented instances exist of German armor withdrawing from urban areas or hedgerow country specifically to avoid PIAT ambushes. The psychological impact exceeded the weapon's actual kill rate. German tankers understood that PIAT teams in close terrain represented lethal threats that could not be suppressed easily with machine gun fire, and that required infantry support to eliminate. The most famous PIAT engagement occurred at Arnhem in September 1944 during Operation Market Garden. Major Robert Kane, commanding a composite force defending Arnhem Bridge approaches, personally destroyed or disabled 6 German armored vehicles using a PIAT over 4 days of continuous combat. Kane's shoulder was severely injured from repeated firing, but he continued operating the weapon. His actions demonstrated both the PIAT's combat effectiveness and the physical toll it exacted on operators. Kane was awarded the Victoria Cross, one of the few British soldiers so honored specifically for PIAT employment. Comparison with the American and German infantry anti-tank weapons reveals the PIAT's distinctive characteristics. The American bazooka was lighter, easier to operate, and had better range, but required backblast clearance of approximately 10 meters behind the operator. The German Panzer was more powerful, but heavier, and produced even more severe backblast. The Panzer was simpler and cheaper, but single-use only. The PAT's reusability, lack of backblast, and shaped charge effectiveness made it superior for defensive operations in close terrain despite its operational difficulties. British infantry doctrine emphasized the PAT's advantages in static defense and urban combat while acknowledging its limitations in open warfare. Production totaled approximately 115,000 units between 1943 and 1945. The weapon remained in British service until the mid-1950s and was used extensively during the Korean War, where it proved effective against North Korean T-34 tanks in urban combat. The weapon was gradually replaced by more modern recoilless rifles and wire-guided missiles, but its basic concept, spring propulsion eliminating backblast, was vindicated by combat performance despite operational complaints. The limitations were substantial and well documented. The severe recoil caused injuries that reduced combat effectiveness. Soldiers learned to pad their shoulders with extra clothing and to fire from supported positions when possible, but this was not always feasible. The manual cocking requirement for the first shot exposed operators to enemy fire. The low muzzle velocity meant the bomb dropped significantly in flight, requiring extensive practice to achieve hits beyond 30 meters. The shaped charge was sensitive to impact angle. Glancing hits often failed to penetrate. The weapon's weight made it exhausting to carry during long movements. Most soldiers assigned PAT duty considered it a punishment detail. Psychological research conducted after the war identified interesting patterns. German tank crews reported higher stress levels when operating in PAT-favoring terrain compared to operating against bazooka-equipped forces, despite the bazooka's superior range and ease of use. The PAT's silence and lack of visible signature meant that tank crews often did not know they were under anti-tank fire until the impact occurred. This uncertainty created persistent anxiety that affected tactical decision-making. German armor doctrine evolved to avoid close terrain and urban environments where PAT effectiveness was highest, demonstrating that the weapon's psychological impact exceeded its statistical lethality. Post-war analysis confirmed that the PAT destroyed or disabled more German armored vehicles per weapon issued than any other British infantry anti-tank system. Exact numbers remain disputed, but estimates suggest approximately 1 armored kill per 3 PATs deployed in combat, a remarkably high ratio given the weapon's limitations. This effectiveness was derived not from superior technology, but from tactical employment that exploited the weapon's unique characteristics while accepting its severe operational drawbacks. The soldier in the Normandy hedgerow who destroyed the Panzer IV likely suffered a shoulder injury requiring medical treatment. He may have been unable to participate in subsequent combat operations. The tank he destroyed was one of thousands disabled by PAT fire during the Northwest Europe campaign, contributing to German operational failures that derived partially from the armor's inability to operate effectively in close terrain, where PAT ambushes were probable. The weapon that made German tanks turn around on sight was not superior to alternatives in range, accuracy, or ease of use. It succeeded by being usable in tactical situations where other weapons could not function, and by creating uncertainty in enemy armor operations that forced tactical adjustments favoring Allied infantry. The bruised shoulders and fractured collarbones of thousands of British soldiers was the price paid for this tactical advantage, a price they paid reluctantly but effectively.